Pleasant morning to one and all. I'm Dr. Sumitra. I'm here to present you about the process synchronization in operating system concept. The process synchronization is where we will be discussing about the basic background, the critical session problem, and the Peterson solution. Synchronization's hardware, mutex, locks, and semaphores, classical problems of synchronizations, monitors, and synchronization example, alternative approaches. So we'll be discussing all this topic right now, and the main objective of this having process synchronization is all about to present the concept of the process synchronization, where it introduces a critical section problem whose solutions can be used to ensure the consistency of a shared data, and it also presents both hardware and the software solutions of the critical section problems, and to examine several classical process synchronization problems, and to explore the several tools that can be used to solve the process synchronization problems too. And the basic background behind this problem solving of process synchronization is where the process can execute concurrently, and it may be interrupted at any time, partially completing the execution, and the concurrent access to shared any data may result in your data inconsistency, and it's also maintain a data consistency require the mechanism to ensure the orderly execution of a cooperating process. And basic illustrations of the problem, suppose we want to having a provide a solution to the producer consumer problem that fills all the buffer, and we can also do by having an integer counter that keeps a track of the number to fill the buffers. Initially, when the counter set it to 0, it is incremented by the producer after it produces a new buffer, and is incremented by the consumer after it consumes a buffer. And whereas a producer is all about, while when we take the condition as a true, produce an item with the next to produce, while the counter is double equal to the buffer size, do something. The buffer of n is equal to next produce, in is equal to in of plus percentage of buffer size, and counter plus plus. The consumer is all about while of true, while counter double equal to 0, and I do nothing, and next consume the buffer of out. Out is equal to out plus 1 percentage of buffer size. A counter will be decremented, and hence it is consumed in the next consumed manner. When we have a say raise conditions where we can increment the counter of plus plus, which could be implemented, and we have an integer plus is equal to counter, and integer 1 is equal to, we have to increment the integer plus of 1, and counter is equal to integer of integer 1, and the counter was decremented when the integer 2 is equal to counter, integer 2 is equal to integer 2 minus 1, and the counter is equal to integer 2. Consider this executions of interleaving with the count is equal to 5. Initially, the producer executes integer 1 is equal to counter when we have a register 1 is equal to 5, and the producer executed the register 1 is equal to register 1 plus 5, and the consumer executed the register 2 is equal to counter, and the consumer executed the register 2 is equal to register 2 minus 1, and we also produce the producer executes a counter is equal to register of 1, and the consumer executed the counter is equal to register of 2, where we have a critical section problem. And this critical section problem consider the system of n process of p0 to p1 up to p of n minus 1, and each process has a critical section segments of a node, and each process may be having a common variable, updating the table, writing files, and so on. While one process in a critical section, no matter how it is in a critical section, and this critical section is to design the protocols to solve the each processor must ask the permissions to enter the critical sections. In entry sections may follow the critical sections with the exit level, and the remainder sections too. The critical section is ways do of entry of section, critical section, exit of section with the remainder section, while of true. Algorithm for the process of P, I do of while a return is equal to J, critical sections, and turn is equal to J of a J, reminder section, while of true. The main solutions for this critical section problem is all about the mutual exclusion process and bounded waiting, and so on. The mutual exclusion, if the process of Py is executing in its critical section, there are no process can be executing in their critical sections. The process, if no process is executed in its critical section, and there exists some process that wish to enter the critical sections, and that process or selection of the process that will enter the critical sections next can cannot be postponed immediately. The bounded waiting, a bounded may exist on the number of bounded times that other process are allowed to enter the critical sections. After the process has made a request to enter the critical sections and before the request is granted, consume that each process executes at the non-zero speed and no conception concerning a relative speed of the end processor. And the critical section handling in an operating system, there are two approaches depending on its if the kernel is primitive or non-primitive. And the primitive is where it allows the preemptions of the process while running in a kernel mode, and the non-preemptive process run until it exits the kernel mode, blocks and voluntarily yields a CPU, essentially free of race conditions in kernel modes. And the Peterson solutions, where it's a good algorithmic descriptions of solving the problem, and two process solutions, assuming that the load and the store machine language instructions are automatic that automatic that and that cannot be interrupted. The two process shares two variables, int of turn, boolean of flag of two, and the variable turn indicates while I turn it into the enter the critical sections, and flag of carries arrays used to indicate if the process is ready to enter the critical section, and it implements a process of pi is ready. And here is a process for the process of pi to a flag of I is equal to true and true turn is equal to j, while flag of j and the return of j is equal to with the critical section, and the flag of I is equal to flash false and the remainder sections while of true. The Peterson's execution is all about proves that there are three customer requirements are met, the mutual exclusion is preserved, and the pi enters your ci only if it either a flag of j is equal to false or turns into an I. The process requirement is satisfied and the bounded waiting requirement is met. The synchronization's hardware is where very many systems provides a hardware support for implementing the critical sections code, and all solutions below an idea of locking or protecting a critical sections via the locks. Uniprocessors could disable the interrupt. Currently running code could execute without interruptions. Generally, too, if inefficient or the multi-core processor operating system using this not broadly scalable, and the modern machines provides a special automatic hardware instructions, and either test memory words and set the values or swap the content of two memory words. A solution to the critical section problem using a lock. Do acquire a lock, a critical sections, release the lock and the remainder sections while of true. And here the test and test instructions definitely with a boolean test in the set of boolean target, and the boolean is equal to targeted, and the target of the true turns a return and executed automatically and returns your original value for past parameters, and set the value of the past parameters to the true. The main solutions using the test and the set of is to share the boolean variable lock initialized to the false, and the solutions for this could be of do while of test and set locks and critical sections, and the false is equal to your false conditions and the while of true conditions. And we can also comparing then the swapping instructions. So basically we can execute it and returns the original value for past parameter values and set the variable values and values of the past parameter and the values, but only if the values to executed, which can also be swapped over there. And the solutions for comparing and the swapping is all about we can integer the lock initialized to the 0. That could be the exact solutions of this. And we can also have a mutex locks is where we can previously solutions are complicated and generally inaccessible to the applications per programmer. OS designer builds software tools to solve the critical section problems, and the simplest is mutex of solution and protects the critical sections by first, and calls to the acquire and the release of statements may be automatic. I hope you are clear with this concept. Thank you.